Okay, so in our previous video, we kind of talked about uh, a strange universe where, you know, you could call it a kind of a topological universe if you wish. Okay, maybe a fancy name for it. So in this topological strange universe, like everything is made up of an extremely flexible and elastic material, say some kind of rubber in which you can, if you wish, you can take an object and expand it, shrink it, you can turn it, and you can test it, twist it actually, okay, as much as you like. So, so, so in other words, that if you, for example, take an object and um, and you distort it by some continuous transformation. In other words, that you apply some kind of continuous distortion onto it, um, and you're going to get obviously a new object actually. As a result, you're going to get what you call a new object, but this new object is really essentially fundamentally same as the original what you call object. For example, if you take say a flower in this strange universe with three petals, okay, and if you, for example, shrink it, okay, um, or maybe make it even bigger, expand it, okay, and maybe, you know, uh, turn and twist it, okay. You can make petals big and small, doesn't matter. Even you can make these petals a bit of the wiggly petals actually, because when you are creating these wiggly petals, actually, what actually you're doing is that you really are turning and twisting, you know, the curves on the petals actually. Okay, so applying any kind of continuous distortion onto any object would produce a kind of an equivalent object actually, okay, which is fundamentally same. So in other words, all of these objects are basically fundamentally, equivalent to each other. Another intuitive way to understand this, that what do you mean by that all of these objects, which apparently looks like different, actually are fundamentally equivalent to each other, is that if you, for example, a kind of a bug, actually a small bug, okay, maybe a bug or maybe an ant who's moving on, this petal actually, okay, then it, being a bug, if you move on, for example, this petal or this part of the flower or this petal, essentially you would not feel any difference actually. So you'll feel like you are moving on a, kind of a, you know same object actually. Okay, though globally, though if you see these pictures, from above, actually they look like different. But for a bug, actually they are not going to be essentially different actually. And we named this property of being equivalent as equivalence by distortions actually. So equivalence by distortions. So if you also want to give it a kind of a fancy name, so you can call it topological equivalence actually. Okay, so it's kind of topological equivalence. So in other words, all of these flowers are topologically equivalent. If you are a bug moving on any of these flowers, actually you will not feel any difference, though there is, apparently, you know a different. So topologically they are the same actually. Okay, so now we like to move towards uh, an interesting question, which is really the opposite of it. So we saw that what is the meaning of equivalence by distortion or topological equivalence of two objects, but you can ask a question actually, that when two given objects, two given objects in this strange universe made up of the flexible material are not topologically equivalent or equivalent by distortions actually. Topologically equivalent actually. Okay, so another intuitive way to understand this is that, okay, if you have been given two objects and you are a really, for example, small bug moving on to the both objects, then you know then by just moving on both objects, okay, can you spot some differences? So if you're able to spot some differences, then probably you are moving on to the two different objects actually. If you're not able to spot any differences, then probably you're moving on some kind of topologically equivalent objects actually. Okay, so the way to do it, the recipe of knowing that whether the given objects are not topologically equivalent, uh, we know how to know the topological equivalence, but now we like to focus at under what conditions the two objects are not topologically equivalent. So for example, so the recipe is this actually. So the recipe is this. You know, the easiest way is this, that add or take away, for example, some points, say out of some points or piece out of uh, both objects, both objects, and see you get the same number of pieces or not. You get same number of parts or not. So if not, imagine that you took away some points from the both objects, and it turns out that both objects have been separated into kind of different number of pieces, then probably they are not topologically equivalent actually. So let me illustrate this through, for example, an example actually. So let's take, for example, a circle, okay, made up of the flexible material, and let's say a circle and say a curve attached to it, for example. Okay, now the question is this you know um, are these both objects, for example, same, um, or not topologically? Okay, so one way to know is, the easiest way to know is that, okay, remove some points from this object. For example, if I remove this point from object, okay, maybe I removed it, and I remove, for example, one point out of this object, how many pieces I'm getting? So you can say that, okay, like after removing this point, the curve is kind of a one piece actually. And how about this curve? So this curve is also what do you call one piece. But how about if I, instead of taking, okay, let me put back, and instead of taking the points, say for example from here, I take a point, say for example from here actually. So I remove the point from here. Okay, now I can see that by removing, say for example, one point from here, this object is now turned into two parts actually. Okay, just like it's turned into the two parts. Okay, so one part is this little part, okay, and the other part is really the rest of the part. While by removing the one part, that like circle turned into one part or one piece, while if you take away this point out of this object, then it turned into the two parts actually, or the two pieces. Okay, so I'm going to say they are not topologically, equivalent actually. Okay, so they're not topologically equivalent. Okay, so they are two different things. They are not topologically equivalent. Okay. So that's example number, for example, 1 actually. Another example could be, so here is another example. Here is another example that how about if I take, for example, a zero curve and a theta curve actually. Okay. Are they topologically equivalent? In other words, if you take some number of points from zero, and if you take away some number of points, it's not necessarily always one. Okay, maybe taking away 1 point would not work. Then you are also allowed to take some number of points. You can take 2 or 3 points and so on and so forth. For example, if you take 1 point, say this point out of circle 0, then this 0 is one piece. How about if I, for example, take 1 point out of theta? So theta is still what do you call a one piece actually. Okay, so if I take some other point, say out of theta, let me redraw theta. Okay, say I take away, for example, a point from here actually, then you can still see that, okay, this is one part actually. Okay, so this is still, it's one part. It's not really two parts actually. So no matter, so so no matter, so let me redraw theta again. So no matter from where you take away 1 point, you still get what do you call one piece actually. Okay. Um, so does this mean that they are topologically equivalent? Not necessarily. Why? Because now instead of taking 1 points, for example, if I take 2 points out of circle and then theta as well actually. Okay, so let's first of all take away, so let me redraw, for example, 0, and this is my what do you call theta curve. Okay, and I take for example 2 parts. So I'm taking this part, for example, 1 point, and I'm taking another point here actually. So by taking away 2 points, I'm getting what you call two pieces actually. So I'm sure you can see that you are getting the two parts or two pieces of the theta curve. How about if I take away now 2 points from here? So like 1 point from here and 1 point from here actually. So how many pieces are these? You can still see that, okay, so one thing that obviously now you can see that it's a one part actually, it's a one piece, like it's a one piece actually. Okay, so here by taking away 2 parts you are getting two pieces, but here by taking away 2 parts, 2 points, you're getting still one piece actually, or one part. Okay, and that's really an evidence actually that these two objects are not topologically equivalent. Because if they will be topologically equivalent, whatever you do here and whatever you do here should not give you a different number of pieces actually, should not give you different picture. Okay, another way to look, for example, this, so you can also see that if I take again what you call theta curve, and instead of taking, for example, these 2 points, I take away these 2 points actually where this is attached. Okay, and now you see that how many parts you get. So by taking away 2 points, you are getting your curve, the theta curve is turned into 3 parts actually. Okay, so here you take away 2 points, and no matter from where you take 2 points, take away 2 points from the zero curve, you will always get what you call two parts actually. But here, by taking away the different 2 points, you are getting the different number of parts of the curve. So that's an evidence actually to show that the zero curve fundamentally is different from the theta curve actually. Okay, the symbol 0 is different from, you know, fundamentally different from you know theta curve actually. Okay, so one quick exercise for you. So here is a little exercise for you. Okay, is to basically, for example, write all A, B, C, D letters up to say Z, and find out that which of the two letters out of, you know, all these letters are equivalent to each other. In other words, which of the letters are equivalent to each other and which of the letters are not equivalent to each other. So, you know, try to compare, what do you call, try to treat these ABCs as curves and try to know, you know, through this recipe by taking away some points, you know, that whether, you know, A is topologically equivalent to what, or B is topologically equivalent to what, or C is topologically equivalent to what. Okay. So for example, you can immediately see actually that, okay, you know, the C and Z should be topologically equivalent. So if this thing is made up of a rubber band, you can really create corners and turn it into what do you call Z. So they look good actually. Okay, so they look topologically equivalent. But how about others actually? So it would be a very good exercise. So take away. So if you're comparing two objects, two alphabets from ABC, take away some number of points and try to show that by taking away the same number of points, you are getting, what do you call, two different, you know, two different curves actually. Okay. Well, another example, which is really a 3D example actually, which is a 3D example. So you can take, for example, any two objects right in front of in your room, and you can ask that, okay, whether these two objects are topologically equivalent or not. Okay, are they equivalent by distortions or not? So answering that they are equivalent probably seem easy, but answering that they are not equivalent, you know, is a bit trickier actually. Is a bit trickier. Okay, so for example, let's take two examples. So let's take a 3D, you know, sphere. So that's really the sphere, 2D sphere sitting in a 3 dimension. And let's take, for example, a donut actually. Okay, let's take this donut. And ask a question that whether they are topologically equivalent or not. Okay, so what we can do in order to know that they are topologically equivalent or not, you know, you can take, say, some points out of, for example, this sphere and some points out of this donut and see that whether you get the same number of pieces or not actually. Okay, so for example, I'm taking one chunk of points out of surface of sphere actually. So let me take a, you know, closed loop onto the surface of sphere. Okay, and say I removed this. Okay, so I kind of removed this. Let me copy and paste it. Okay, copy and paste it. So I kind of removed you know, this part out of, what do you call, the surface. Now you have the two parts. You have turned the pictures into the two parts. So one part is this, in other words, sphere without this patch, and other part is really this, something that you have taken away actually. Okay, something that you have taken away maybe after removing, you know, the inside of the, say, sphere looks like yellow. Okay, so it's really the two parts, right? I took the sphere, I created a closed loop, a closed curve onto the sphere, and turned it into and cut this piece out of the surface of the sphere actually. And as a result, I'm getting what you call the two parts. So one part is this and other part is this. How about if you take, for example, a closed loop onto the donut actually? Okay, so let's take, for example, a closed loop onto the donut. Okay, and you cut it from this closed loop actually. So you slice it from this closed loop. So when you're going to slice it, how would how it would look like actually? Or if you take away, for example, this part out of donut, the donut will split into something like this actually. So I hope that you agree with me that the donut would now look something like a tube actually. Okay, something like, okay, a tube. Okay, something like a tube actually. So if I take away this part, so imagine that, like, all I took away this part, so I sliced the donut from here. So I'm gonna turn, and I took away, for example, this slice out of it. This is going to turn the the donut into, what do you call this, tube actually, or maybe it's like a molded cylinder. But this thing is really one part. Okay, it's not two part. So I took a closed loop from sphere and took it away, cut it and took it away. I got two parts. And for example, if I sliced this patch out of, what do you call, a donut, my donut turned it into, what do you call, a single piece actually. So it's really still is a single piece actually. So by taking away one loop from here, you get two parts, and taking away one loop from here, you are getting, what do you call, a one part. So this shows that the sphere is not, topologically equivalent to, what do you call, donut actually. Okay. So in other words, if you want to know that two objects are topologically equivalent, do something with one object and the do same thing with the other object, and see, by doing the same thing onto the both object, produces the different number of parts. So if it produces the different number of parts, you're going to say that they are not topologically, what do you call, equivalent actually. Okay, so I hope this is enough to show that, okay, that these two objects are not topologically equivalent. I would like to end this really discussion at um, at a little a quote, which makes really the topology something very interesting. So there is a very famous quote actually, that topologist is a man, okay, or a woman, or maybe it's better to call it a human actually. Okay, let's not be gender biased. Okay, and a human. Okay, who doesn't know the difference, who doesn't know the difference between a teacup, okay, teacup, and, okay, donut. Okay, doesn't know the difference between teacup and a donut actually. So why that's a famous kind of a quote actually. So you can understand this really this notion through this, for example, picture actually, that if you have a donut, okay, and you press, for example, some part of it, and you do the transformation through this. Okay, so it's like by pressing more and more piece down, you can create what you call a teacup. Okay, so in other words, you took the donut and applied some, continuous transformations, continuous distortions. Okay, and you turned it into what you call a teacup actually. So essentially, the donut and the teacup are topologically equivalent actually. Okay, so another way to say that a donut has a one crossing, okay, and the the teacup also has a one crossing actually. So there is one hole here and one hole here. So therefore, the both of objects are topologically equivalent actually. Okay. So I hope that this little video kind of gave you another perspective to look at that when two objects are not topologically equivalent. So yeah, thank you.